Welcome to this session. Today we are going to discuss cyclic groups and related problems. Now, what is a cyclic group? A group is said to be cyclic if there exists an element G belongs to G such that every element of A of G is an integral power of G. That is, A is of the form G power n for some integer n, then the element G is called the generator of the group. That means, suppose if I am going to consider Z is a group, let us say it is having some elements, and whatever any element if I am taking, just I am going to consider one element, let us take G. So that element, every element here, any one element I am taking from this, and with this the powers, integral powers of G, let us say G power 1 represent the first element, G power 2 represent the second element, G power 3 represent the third elements, and so on. G power n represent n elements. Then this group is known as a cyclic group, and you are going to represent all the other elements of the group as the integral powers of G. So we can call G is the generator. G is the generator. So once again I am just repeating. So G is a group. G is a group under some binary operation. So it is not, obviously it is a non-empty set. So we have to collect each and every element in G can be represented as the integral power of some element in G, then such group is known as a cyclic group. So all the elements which are represented the integral powers of some element, then that element is known as a generator of the group. So if G is the generator of a cyclic group, then we are going to represent it. So the generator is represented by like this symbol. We say that G generates G. We say that the element G generates the group G. So, and we are going to represent the generator is with this symbol. Let us say we are going to consider one of the example. See here, W4. W4 is a group. Under the binary operation, let us say multiplication. Now, I am going to consider any one element from this set. Let us take I am taking. I belongs to W4. So then I power 0 is equals to 1. Then I power 1 is equals to I. Then I power 2 is equals to minus 1. Then I power 3 is equals to I square into I. So which is minus 1 into I. So which is equals to minus I. So now I am going to represent all the elements W4, all the elements of W4 as, so first one is 1. I am going to take it as I, what is that? I power 0. Minus 1 I am going to represent I square. And next I am going to represent it as I power 1. And then minus I am going to represent as I cubed. So now this I am going to represent in the ascending order. I am going to write I power 0, I power 1, I power 2, I power 3. So all the elements of W4 can be represented as integral powers of I. So then we are going to say that the group W4 comma into multiplication, the group is a cyclic group, and whereas here I is the generator. I is the generator. So in that way we are going to explain what is the cyclic group. Now let us whether it is having a unique cyclic group or more than one, any cyclic group which is having one generator or more than one generator. So here let us go for one theorem. We are saying that if G is a generator of a cyclic group G, G inverse is also a generator of the cyclic group. Whenever G is the cyclic group of a generator of the cyclic group, then G inverse is also a generator. So let us consider, I am taking A be the any element of G, then A can be written as G to the power of N for some N belongs to Z. So I am saying that an element, if I am going to consider A belongs to G, so this is going to be represented as G power N, some value, some integral power of N, where N belongs to integers. Where N belongs to an integer. Now, so I am going to take like this. So what about A is equals to G power N? A equals to Z power N, which is equals to, I am going to write it as G power minus 1 and whole power minus 1 and whole power N. So G can be written as like this. So this is nothing but G power minus 1 and whole power Mn. So M into N, it is minus N. So I can say that A can be represented as G inverse as well. G inverse also. So we can say that G inverse is also another generator of the group G. G inverse is also another generator of the group G. So whenever G is one generator of a cyclic group, then G inverse is also another generator of the same cyclic group. Okay. Now let us go for the other example. Now it is given show that this is Z comma star whose multiplication table is given. Now we have to verify, and this is given as it is group and under the binary operation star, and now we have to verify whether it is a cyclic group or not. To verify whether it is a cyclic group or not, so first of all we need to find out a generator. So for finding a generator, then all the elements of G, what are the elements? Elements of G are nothing but G elements are here A, B, C, D, E, F. These are the elements of G. Now each and every element can be represented as the integral power of some element. So we have to verify whether it is possible or not. So for that, let us consider, I am just taking B square. So B square is nothing but B into B. So B into B. B square is B into B. So B into B is what is that? It is equals to C. So B square is equals to C. Now I am going B power 1 is equals to B. B power 1 is equals to B. Next B square is equals to C. Now what is B cubed? B cubed is B square into B. So B square already calculated, it is C. C into B. So what about C into B? It is D. So this is D. So B cubed is equals to D. Now B to the power of 4. B cubed into B. So B cubed is equals to D. D into B. So once again D into B. So which is equals to E. So B to the power of 4 is equals to E. Next B to the power of 5. So B power 4 into B. B power 4 is E into B. So E into B. Then it is F. So it is B power 5 is equals to F. B power 5 is equals to F. Next B power 6 is equals to B power 5 into B. B power 5 is already F. So F into B, which is equals to A. Now, see, A is over, then B is already over, C is over, and D is there, and next E is there, and F is there. So what I am going to write, A can be written as B power 6, and B can be written as B power 1, C can be written as B square, D can be written as B cubed, E can be written as B power 4, F can be written as B power 5. B power 5. So this is a B cubed and B power 4 and B power 5. So each and every element of G can be represented as the integral power of B. So this group is known as a cyclic group. And here B is known as, then it's a generator. It's a generator. So the group is the cyclic group and it is having the generator B. Now the thing is whether the generator is unique or not. So for that we have to identify what is the B inverse. Earlier we said that G is a group and G inverse, G is a generator of a group, then G inverse is also another generator. Now we have to verify what is a B inverse, what is a B inverse value. So before finding B inverse, we have to know what is the identity element. Observe here, if I am taking A star A is equal to A I am getting, A star B is equal to B I am getting, A star C is equal to C I am getting, A star D is equal to D I am getting, A star E is equal to E I am getting, A star F is equal to F I am getting. So from this what I am going to say that A is the identity element. Observe this, if I am going to multiply all the elements with A, I am going to get the same elements. So I can say that A is the identity element of this group. Whenever A is the identity element of this group, now we have to identify what is B inverse. So while I am going to calculate where I am going to get in B the identity element, so here it is identity element. So B into F is equals to identity element. B into F is equals to identity element. B into F is equals to identity element, or of course F into B is also identity element. So whenever B into F is equals to identity element, then I can say that B inverse is equals to F, or F into B is the identity element. So what is the B inverse is equals to F. So I can say that there is another generator of this cyclic group other than B, that is equals to F. So I can say that F is the another generator of the group Z. See here I am just taking B into F into B, or that is nothing but the binary operation star. So F into B is equals to I am getting. So B inverse is equals to F. So F is another identity. Let us verify this. Whether it is we are getting all the elements or not. So first one is F will be the same. F power 1 is F, and F power 2 is F into F. So F into F is what about the earlier F into F is? So it is E. So I am getting E. Now F cubed is equals to F square into F. So E into F. So what about E into F is equals to D? So this is equals to D. Then F to the power of 4 is. So this is F cubed into F. So which is equals to D into F. So D into F is, what is D into F is C. D into F is C. Then f to the power of 5 is equals to f power 4 into f. So f power 4 is a c into f. C into f is what? B. C into f is b. So this is equals to b. And similarly, f power 6 is equals to f into 5, f power 5 into f. So b into f. B into f. So b into f is a. V into f is equals to a. Now observe, a is over. Next b is over. C is over. Next d. Where b, c, then d is over. So here d, and e is over, and f is over. So all the elements were represented as the integral power of f. So we can say that f is the energy generator. F is the energy generator. So based on the previous theorem, we can say that whenever the inverse is exist, whenever the inverse will be there, whenever G is the generator, then obviously its inverse is also a generator, another generator of a cyclic group. Now let us go for the other example. Prove that Z4 comma plus is a cyclic and find all its generators. Find out all its generators. Now what is Z4? Z4 is nothing but the congruent classes. Congruence classes under addition. Congruence classes modulo 4. Addition modulo 4. So which is the congruence classes addition modulo 4. That means up to 4. So whenever if we are going to say that it is a 4 means then equivalence class of 0 or congruence class of 0, 1, 2, 3 are the elements of Z4. Z4 is consisting then the equivalence class of 0 and next 1, next 2, next 3. So these are the Z4 is consisting. Now we have to verify all the elements can be represented as the integral powers of some element. Now let us consider any one element. 1 power 1 is 1. 1 power 2 is under addition modulo 4. So I am going to 2 times I am going to add. If it is exceeds 4, then I am going to subtract from 4. Otherwise, I am just taking the same value. So 1 square is 1 I am getting. Similarly, 1 cube is 1 plus 1 plus 1. I am getting 3. 1 power 4 is 1, 1, 1, 1. So which is equals to 4. So 4 minus 4. It is under addition modulo 4. So 4 minus 4 is equals to 0. So 0 I am going to represent it as 0. I am going to represent it as, this is congruence class 4, power 4. 1 I am going to represent it as power 1. 2 I am going to represent as power 2. And then this is 3. So we can say that this is a cyclic group. This is a cyclic group where 1 is the generator. 1 is the generator. Now we have to find out the other generator. So which is nothing but the inverse of the, if G is a generator of a cyclic group, then G inverse is also a generator. G inverse is also a generator. So 1 inverse is also a generator. What is 1 inverse? What is a 1 inverse? So this is nothing but 4 minus 1. So which is equals to 3. So 3 is the other generator. 3 is the other generator. See here, 3 is the other generator. So if you want to verify, you can verify whether 3 power 0, I am going to 3 power 1, this I am going to take it as, this I am going to consider it as 3 power 1 is 3, then 3 power 2 is 3 plus 3, so which is equals to 6, which is greater than 4, so it is a 6 minus 4, so then this will become 2. Then this is 3 equivalence class 3 whole power 3, so it is a 6 I am getting 2, 3 square plus 1, or else 2 plus 3 it is 5, or this is a, okay, you can take it as like this, 3, 3, 3, or 3 square plus 3. So 3 square, these two are already, this is 2 and the next 3. So this is equals to 5. So which is 5 minus 4, it is 1. Then similarly 3 power 4 is, so it is 1. Then 3 power 3 is 1. I am going to write like this. So it is 3 power 3 plus 3. So this is 1 and the next 3. So which is equals to 4. So 4 minus 4, which is equals to 0. Which is equals to 0. So I am representing, this is 3 power 4 is 0 and 3 power 3 is 1, 3 power 2 is 2 and 3 power 1 is 3. So I can say that 3 is the another generator. So one is generator is 1 and another generator is 3. Another generator is 3. Now let us go for the other one. See, this is the additive modulo. Now multiplication modulo 5. Multiplication modulo 5. So here prove that Z5 star is a cyclic group and find all its generators. Find all its generators. So here also simply Z5 star which is consisting multiplicative modulo 5. So it is starting with adding 1, 2, then 3 and 4. These are the elements will be there in this set. Now we have to verify under the multiplication modulo 5 whether it is a cyclic group or not. So for that we are taking one generator, let us say 2 power 1, it is 2 and 2 power 2. Earlier problem is additive modulo, so we are going to add here multiplicative modulo. So we are going to multiply, see here 2 into 2, 4. If it is exceeds 5, we are going to divide with 5 and we have to consider the remainder. Otherwise, the same number we have to consider. So 2 power 3 is 8. 8 we are going to divide with 5. So remainder is 3. And 2 power 4, it is equals to 16. Divide by 5 and the remainder I am going to get 1. So 1, then 2, then 3, then 4. So what I am going to write this as 1 is equals to, this is 2 power 4 and 2 is equals to 2 power 1 and the next 3 is equals to 2 power 3 and the next 2 power 4 is what I am going to get, it is 2. So now this is the generator. So now what is the other generator? Now for finding the other generator, inverse of this. What is the inverse of? 2 inverse is nothing but, so where we are going to, for what value we are going to identity, then the corresponding, see I am just taking 2 into 3, I am going to get 6. I am going to get 6. So 6 is more than 5. I am going to divide with 5 and the remainder I am going to get 1. 1 is the identity element. So what is the 2 into 3 or 3 into 2? So I am going to get 1. So 2 inverse is equals to 3 or 3 inverse is equals to 2. So the other 2 inverse is equals to 3. So now 3 is the other generator. So one generator is 2 and other generator is 3. Now suppose it is given, show that the group is a cyclic and how many generators it is having. So it is given a group, G is a group. So this is this is the element. The set is consisting 1, 2, 3, 4, 5, 6. G is consisting, the elements are 1, 2, 3, 4, 5, 6. Now, what is the binary operation? This is modulo 7. So multiplication. Then we have to verify whether it is a cyclic group, and then what is the what are its generators? What are its generators? Okay. So now what is let us consider for this earlier problems. So find out what is the generator. So generator is nothing but, so 3 power 1 if I am taking, it is 3. 3 power 2 is 9. 9 I am going to divide with 7. So whatever the remainder I am getting like this. And the next 3 cubed. 6 is less than 7, no problem. And it is more than 7. Once again, if I am going to 6 into 3, 18. 18 if I am going to divide with 7, the remainder is 4. Remainder is 4. Then 3 power 5. So 4 into 3, it is 12. It is 12. 12 by 7. The remainder is 5. And the next 3 power 6. 3 power 6 is 5 into 3. So it is 15. Divide by 7. So I am going to get 1. So what I am going to write this as 3 power 6. 1 as I am going to write 3 power 6. 2 I am going to write it as 3 square. 3 I am going to write it as 3 I am going to write it as 3 power 1. 4 I am going to write it as 3 power 4. 5 I am going to write it as 3 power 5. And 6 I am going to write it as 3 power 3. So now I am going to represent this in the ascending order. 3, 3 square, 3 cubed, 3 power 4, 3 power 5, 3 power 6. That were mentioned here. Each and every element of G can be represented as the integral powers of 3. Integral powers of 3. So we can say that 3 is the generator. 3 is the generator. Now the another one I am going to say that what is the order of G is? What is the order of G is? 6. Order of G is equals to 6. The number of see here up to 6. So whatever the numbers if I am going to select, then which are relatively prime, then we can say that is also another generator. It is also another generator. So I am taking 2, 6. 2 if I am taking 1 I cannot take, 2 I cannot take, 2, 6. Now it is not a prime number. 3 is not a 3 to 6, no. Next 4 to 6, no. Next 5. So 5 is the prime to 6. 5 is the prime number to 6. 5, 6 if it is divisible by only 1. So I can say that 5 is the prime to 6. So 5 is another generator. 5 is another generator. So I can say that this 5 is also another generator of this cyclic group. Now here some of the concepts are the same based on this. Say let us say every cyclic group is an abelian group, but the converse is not true. Every cyclic group is an abelian, but the converse is not true. Every subgroup of a cyclic group is cyclic. Every subgroup of a cyclic group is a cyclic. Then every element of a group generates a cyclic group which is a subgroup of G. If A is a generator, then A inverse is also a generator. Then if A is a cyclic group generated by an element A of order n, then A power m is another generator if and only if GCD of m comma n is equals to 1, or we can say that m and n are relatively prime. So which is the similar to the last problem. And so here these are the some of the properties of a cyclic group. And see the last one is cyclic group G generated by an element of order n. A power m is also a generator of G if and only if the GCD of m and n is equals to 1. Greatest common divisor, if it is equals to 1, then we can say that. That is also another generator. Let us go for the other one. Let us say here it is given directly the order of a group, of a cyclic group order is given. 8. So up to 8, how many elements that we have to consider? So if I am taking a power 2 is the generator or not? A power 2 is not generator because A2 and 8, the GCD is equals to 2. So which is not equals to 1. They are not relatively prime. So which is not a generator. Then A power 3 if I am considering A power 3, which is 3 is relatively prime. 3 is relatively prime to 8 because the GCD of 3, 8 is equals to 1. So this is a 1 generator. Then another generator, A power 4. A power 4 is not the generator because 4 and 8, the GCD is not equals to 1. So it is 4. So which is not the generator. And the next A power 5. So now 5, 8, which is relatively prime because the GCD is equals to 1. So this is also a generator, another generator. Then A power 6 is not relatively prime because the 6 and 8, the GCD is not equals to 1. So this is not the generator. And A power 7 and 8, they are relatively prime. So now A power 7 is also another generator. So totally how many generators it is having? Or 3 generators it is having. One is A power 3 and A power 5 and A power 7. So it is having 3 generators. One is A cubed, A power 5 and A power 7. So these are the 3 generators of the given cyclic group. So in this way, we are going to find out. We can say in this class what we discussed. What is a cyclic group? So cyclic group can be expressed as a group is said to be cyclic if every element of a group can be represented as the integral power of some element of that same group, then we can say that that group is a cyclic group, and all the elements, if you are going to represent as a integral powers of any one element, then that element we are calling it as a generator. And of course, G is a generator of a cyclic group. Then automatically we can say that G inverse is also another cyclic group. Now let us so another one is if order is given. Completely it is based on the fifth node. So because some of the theorems which are not in our syllabus, so I'm just highlighting those things only, and I'm using those concepts, and I'm going to skip the proof of that one. So here, if any G is a cyclic group which is consisting, the order is given. Suppose if they are asking us to find out what are the all possible generators, in such a case, we are going to find out A to the power of M and A to the power of N. M and N are relatively prime or not, we have to verify. If they are relatively prime, then A power M is also another generator. Like that, we are going to see here, there are 8 elements will be there. So now we are going to verify A power 2 is not relatively prime, so it is not a generator. A power 3 is a relatively prime, so it is a generator. A power 4 is not a relatively prime, it is not generator. A power 5 is a relatively prime. So it is like that. We can say that a cubed, a power 5 and a power 7 are the relatively prime to 8. So we can say that the cyclic group of order 8 will have 3 generators. So here, if you want to express, you can express like this: a power 3 whole power 1 is a power a power 3. A power 3 whole square is a power 6. 3 plus 3, then it is equals to a square. Like that we can calculate, and we are going to get all the generators of a cyclic group. Okay, so today we are going to conclude this topic, this cyclic group, and in the next class we are going to discuss what are the permutation groups, and one or two related problems, and we are going to concentrate on the next topics, homomorphism and isomorphism between the groups, and all we are going to discuss in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.